in this section we want to iterate the notion of derivatives. Namely, we want to form derivatives of derivatives, then derivatives of derivatives of derivatives, and so on, which are then called the higher order derivatives of a function in case they exist. One of the main results of this section will be Taylor's theorem, which is a very important theorem to use higher order derivatives to approximate complicated functions which are differentiable by simpler ones, namely by polynomials. We will see this later on, but first introduce all the terminology for higher order derivatives. Before I do so, I apologize that I'm back in this room with the not that fancy camera again. The problem is that now in this lockdown situation, it's not that easy to contact your colleagues and to reach your colleagues about getting cameras, so I simply don't have access to a good camera yet, so I just have to rely on this room. Sorry about that. Okay, I start straightforwardly by introducing these higher order derivatives. Okay, we're at definition for 30. And following situation, we have some interval called I, and we have some function defined on this interval taking values in C, and we assume that the function is differentiable. Okay, and one piece of notation, we put f, and then as an exponent, a 0 in parentheses. This is simply denoting the function itself, and we will see that this we will replace this 0 by other numbers in the what's to come. So we will see why this fits in this framework. Okay, first of all, part A of the definition. The function f prime going from I to C. So simply x is mapped to simply the derivative here, f prime, which associates to each point the derivative of f at this point. This is called the derivative. Derivative of f. Okay, now I think everyone has the same questions on her or his mind. Why is he doing this? We have already seen this. We have already. Yes and no. We have introduced derivatives, but derivatives at a point. I've always called something f prime of x0 or of a the derivative at the point a. Here I'm now introducing this as a function, which really associates to each point the derivative at that point as a function, and this is simply called the derivative, and not at a particular point. And this is, very strictly speaking, I haven't introduced this yet. So this is why I'm including this in this definition. And we include the notation f in the exponent 1 in parentheses. This is simply supposed to be f prime. Okay, now we come to higher order derivatives. As I said, we have derivatives of derivatives, and I will introduce the second derivative explicitly and then do the, introduce the general case recursively. So first of all, I say that f is twice differentiable in a point a in the interval. So twice differentiable in a, if the derivative, which exists since the function is assumed to be differentiable, if this as a function is again differentiable in the point a. So the function is once differentiable everywhere, and then second time also in the point a. So the derivative as a function is again differentiable. Okay, then we put the second derivative in a, which is f double prime, so f prime prime of a. This is simply supposed to be the derivative of f prime in a, which then formally is defined like this. So, and this is called the second derivative of f in a. Probably most of you have seen this already in high school. The second derivative of f in a. Okay, in physics this has a nice interpretation. You've probably seen this in the theoretical physics course where you talked about theoretical mechanics. There it's the idea that if you have some curve or some particle moving or some number developing as a function on an interval, we know that the first derivative is the slope or the velocity of the thing, and the second derivative is then the acceleration in physics. This is what you've probably seen at this point, so I won't elaborate on this anymore, not too much, but yeah. So this is the second derivative, and we call f simply twice differentiable without respect to a point if, twice differentiable if it is twice differentiable in A for every A. Same as with differentiability. In A for all A in I, or I could just say, to be a bit simpler, if the derivative is differentiable without reference to a point. Okay, and we put f2 in parentheses to be the second derivative as a function I to c, assuming that it exists, so that f is twice differentiable. Okay, now the general case. How do I define all higher order derivatives? This is now what I can do recursively. Namely, I assume that something is k minus 1 times differentiable and define what it then means to be k times differentiable. This is basically what I did here in the case k equal to 2. So part C of the definition, we assume we have some number k in n, which is 3 or bigger. We say that f is k times differentiable in A if, and now we basically model the definition of the second derivative, if we assume that we already know what k minus 1 times differentiable means, and if we assume that f is k minus 1 times differentiable, so everywhere, and the k minus first derivative, which I denote by f to the k minus 1, I say a bit on this in a second. So this as a function from I to c, this is again differentiable in the point A. Okay, so if we know that this this function exists, then we put the kth derivative, which we write here in parentheses, f to the k of A is to be defined, and now you can guess what's coming, the k minus first derivative prime in A. So derivative of the k minus first derivative. And now, of course, this looks a bit awkward because we don't know what this is, but as you can see, we can do this now recursively because we always kind of increase k by 1. We have the second derivative, which was defined there explicitly. Now to get the third derivative, we have to insert k equal to 3 here, and this means f is 3 times differentiable in A. If, first of all, f is k minus 1 times differentiable, so twice differentiable as a whole function, and the second derivative, f2, so which I defined there, is differentiable in A. Then we get the third derivative, then f to the 3 of A is the derivative of f2 in the point A. Okay, then we've got the third derivative, and now we can do the fourth derivative. We can say that, of course, then f is k times f is 4 times differentiable in A, if it is 3 times differentiable, and if the third derivative is differentiable in A. Then we have the fourth derivative as the derivative of the third derivative in A. And so on and so on and so on and so on. So we can just iterate the construction here, and the only thing that's missing here, we could just call f k times differentiable without giving a point. If it is k times differentiable in A for every A. Okay, so assuming all these derivatives exist, then we can just do this again and again and again. This is the idea behind this definition. And then, now, one more notion. We call f smooth if it is differentiable as often as we want, so infinitely times differentiable, so to say. And formally speaking, this is if it is k times differentiable for all k in n. Okay, a smooth function, which is a very common term also in physics. Okay, so these are the derivatives here, and just some additional notation I just want to put on here. The third derivative, which is now, which we have seen now here as f to the exponent 3 in parentheses in a at some point. This is also written sometimes by taking just f prime prime prime, so 3 of these dashes here of a. So this is defined as this, and this expression is explained above. And the same we do sometimes with the fourth derivative, prime 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 of a. This is then the fourth derivative of a, assuming it exists, but we won't use more primes than that because no one can read this anymore. Okay, let me erase the blackboard, and then we will see some examples and some computations of higher derivatives, some very basic ones. Let's consider one of our simplest examples, namely polynomials. And not only polynomials, I do the very simple case, namely example for 31. The first one is the function going from r to r, f of x is x to the n. Okay, we've seen that this is, oops, sorry, microphone issues again. This function is differentiable, and the derivative of this function was identified as n times x to the n minus 1. And we can see the derivative is again a polynomial. So again, every polynomial is differentiable, so we can differentiate again. The second derivative then again will be a polynomial, so we can differentiate again and again and again. And at some point it will just disappear, so the derivatives will vanish. So this means that f is indeed smooth. And the derivatives, as I said before, so f prime of x is n times x to the n minus 1. So the kind of the slope of the tangent line at the point x has this value. This is, always remember the geometric interpretation. So if we form the second derivative, we have to derive this expression here. And so by our rules for derivatives, constant factors in front, they don't matter, so they just remain. So we have to multiply the derivative of this expression here with n, and this is simply by the same rule as before. F prime of x is then n times, and then the derivative of this guy, which is n minus 1 times x to the power of n minus 2, and so on and so on. Here, assuming that n is bigger than 2, otherwise bigger than or equal to 2, otherwise we would have 0 here. And so on. And the general form is f to the k, so the kth derivative of f at x is n times n minus 1 times n minus 2, and so on, until n minus k plus 1 times x to the power of n minus k. And this holds as long as k is smaller than n, so for all k in 1, 2, until n. And all higher derivatives are just 0. And of course the 0 function is differentiable, so yeah, f to the k of x is 0 for all k bigger than n. So this is a very general form of these, these derivatives. Of course, technically this should be proven by induction, but I won't go into detail here because this is pretty obvious here that we achieved this expression at that point. Okay, this microphone. Second example, also not that complicated, but here we see kind of at some point the derivatives somehow are stabilized because there's just 0 everywhere. But there are also smooth functions that don't have this property, namely another very simple example, g going from r to r. G of x is the sine of x. Okay, we've seen that the derivative of the sine is the cosine. This is what we have computed in the previous sections. So the derivative is the cosine of x. But we've seen the cosine is also differentiable. So the derivative is again differentiable, which means so g prime is differentiable, which means so g prime is differentiable with g double prime, so the second derivative, is minus the sine of x. And now we see, since the sign is differentiable, and since this minus sign here doesn't matter, so for differentiability, so this means that this is again differentiable, and we see that this will again be derived by as the cosine, then we will get the sine again, and so we kind of hop between sine and cosine, just that the sine, so the sine SIGN is changing all the time. And so there's a general formula for this, but this needs to be proven by induction, which I won't do here because it's very, very simple actually. Prove by induction that f is smooth, so it's k times differentiable for each k, and this is then shown by induction over k. Sorry, not f, g. G is smooth, and the derivatives have the following general form. G, the even derivatives, g to the 2k of x, so the 2kth derivative is minus 1 to the k sine x, while f to the 2k plus 1, so the 2k plus first derivative, is minus 1 to the power of k times the cosine of x. And this for all k in n. Okay, so this is now an example of a function where all derivatives exist and none of them is vanishing. Okay, now we will take a first application of derivatives, and we will see I've given you nothing more basically than the definition of the derivative and the first example, which is not relevant for the next thing. But we can already use this notion of higher differentiability and our knowledge about differentiable functions and derivatives and so on from before to prove a really beautiful theorem, which is a kind of famous one which has many proofs and is quite important. And I will give you a proof via derivatives. Theorem 432. This has a beautiful name, namely the inequality between arithmetic and geometric means. Okay, and this is a statement that the statement itself has nothing to do with derivatives. But the proof then is, in my opinion, quite beautiful. Namely, there's a simple inequality that holds. If I take the nth root of a product of n different non-negative numbers, this expression here, if a1 to an are non-negative numbers, this is always smaller than or equal to a1 plus a2 plus and so on plus an divided by n. And this holds true for all a1 to an in the interval from 0 to plus infinity, and for all n in n. Okay, this left-hand expression here, this is called the geometric mean of the numbers a1 to an. And this here is called the arithmetic mean. Of a1 to an. Okay, and before I give you the proof, I want to discuss these expressions a bit because they have some really interesting interpretation. Let me do this in form of a remark. So remark for 33. Oops. So first of all, what are these expressions? So if we take a look at this on the right-hand side, this is actually not that complicated. The arithmetic mean is the number that we usually take when we want to discuss the average of some numbers. We just add them up, all of them, and then divide it by the number of summons here. For example, if I would have a lecture hall of students here, and I would have, I don't know, 350 students, and I want the average size of the students in this class. So what would I do? I would add all the sizes, all 350, and divide afterwards by 350. The number of this would be the average size of a student in the class. Or if I want to compare, if I want the average price of something in the shop, I would just have something that I can buy in, I don't know, 10 different shops in the town, and I have 10 different prices. So the average price of this item would then be just the sum of these 10 prices divided by 10. This is what we always do. Or the average of two numbers, for example, I just add the two numbers and divide by 2. This is what we kind of intuitively always do when we take the average of numbers. So I just write the usual average. So e.g. kind of an average price. Or if another example, if I have an exam, and in Germany the grades usually go between, at least in high school, they go between 1 and 6. So 1, 2, 3, 4, 5, 6. 1 is the best, 6 is the worst. And if I want the average grade of an exam, I kind of add up all the grades and divide by the number of participants. This is what you do with the average. So yeah, average grade. Okay, the geometric mean is not that obvious maybe at first sight, but this is this also has a lot of applications, and the easiest example to see is that you can use it to take average growth rates. Okay, what do I mean by this? For example, if I want to measure the growth of a population of individuals, some like in biology, some population, or if I want to increase kind of the growth of some money, of some portfolio containing stocks and bonds and so on, let's assume I have, for example, I have some, let's assume this money example. So we have a portfolio with stocks and bonds, which kind of whose value is changing, and I want to see the growth that the portfolio has each year. So if I assume that in the first year, it grows by a factor of A1. So the new value would be A1 times the old value. Then in the second year, I would have A2, which means that in the second year, so compared to the first year, this would be A2 times the sum after year 1 would be the sum after year 2, and so on. And so I get numbers A1 to AN, which are kind of the n different growth factors for the n years that I have this money in the portfolio. And this number here then, this nth root of the product of them would then be the average growth rate. And average in the sense, if I would have this growth rate, the same value each year, constantly, then I would end up with the same amount of money that I have with this varying growth rates. The same with the population. So if I take the growth of the population, and so after year 1, the number of individuals is A1 times the number of individuals that were there when I started watching it, then A2 would be the factor that I multiply the population after year 1 with this sum factor and so on. And so this number here, so if A1 to AM would be these growth rates after in each year. And so this would then be if the population would just grow or shrink by the same amount each year, this would be the value. So this would be the growth factor, that this would be the same. So in some sense, this is really then the average of the growth rates, because if you have these growth factors, this expression is not really meaningful. So you can compute it, of course, but it doesn't tell you anything about these rates. This is much more interesting. And so this famous inequality says now that these two have this relation, so that these kind of growth average, the geometric mean, but this is always less than or equal to this arithmetic mean. Okay, so this is the interpretation, and the proof will be not that easy, and we will see how derivatives come into play. Just one more thing, there's a much simpler proof in the case of n equal to 2. And this proof is so simple that I can do this in 2 lines here. And this is something I could have done much earlier in this class, but somehow it didn't pop up. So we have 2 numbers, and for simplicity I call them A and B, between 0 and infinity. And then I can compute the following. First of all, I know that 0 is smaller than or equal to a minus b squared, because every square is non-negative. This is the same by this binomial formula as a squared minus 2ab plus b squared. Okay, now we have considered this an inequality and forget about this middle term. I just want to add 4ab to both sides. Then we would have 4ab is smaller than, adding 4ab to this expression, a squared plus 2ab plus b squared. And this is now, again by binomial formula here, the same as a plus b squared. Now, if I just bring this, divide everything by 4, I get that we have AB is smaller than or equal to A plus B squared divided by 4. And we have seen in chapter 2 somewhere, I think, that the square roots are monotonic. So here we really get that this, if you take square roots, the inequality is preserved, and I get that the square root of A times B is smaller than A plus B over 2. And this is the inequality in the case n equal to 2. One more remark before I finally give you the proof. This name is a bit lengthy, so inequality between arithmetic and means, that's a bit long to always refer to, and so as a concise name that is quite common and used very often, and I will also occasionally maybe use this. This is also simply called the AMGM inequality. Arithmetic mean, geometric mean. There are more inequalities between, there are more inequalities and more notions of means, but I won't discuss them here. So this is the short name that you can always use when you write down some argument. Okay, now I erase and now I really give you the proof. The proof of this statement is done by induction over n. Okay, so the base case is trivial. This is n equal to 1, and if we look at both sides of the equation, this just a1 is smaller than or equal to a1, which is clear. So this base case is indeed obvious. Okay, now for the induction step. This will now become quite some work. Oops. Step. So we assume, as the induction hypothesis, that for some number n, it holds that the inequality is true for all possible values. So the nth root of a1 times a2 times and so on times an is smaller than or equal to a1 plus a2 plus and so on plus an over n for all a1 to an in 0 to infinity. Okay, and now to make this explicit, what do we need to show? So we need to show the statement for n plus 1. So we want to derive that the n plus first root of n plus 1 numbers, so a1, a2, until an plus 1 is smaller than or equal to a1 plus a2 plus plus an plus 1 divided by n plus 1. So this is what we want to show for all a1 to an plus 1 between 0 and infinity. Okay, then first of all, an observation: if one of these numbers is 0, then the statement is obvious, because then this here always becomes 0 on the left-hand side, and the right-hand side is obviously non-negative, because here everything is non-negative. So there's no need to show anything if the number, if one of the factors is 0. So if there exists some I between 1 and n plus 1 with ai equal to 0, then the statement is obvious again. So we assume in the following that we only consider positive numbers. So assume a1 to an plus 1 are in the open interval 0 to plus infinity. Okay, now what does this have to do with derivatives? The idea is now that we want to consider this expression here as a function, and the variable is then the last of these different numbers. So we introduce a function, and so this is inequality, and we consider just the difference of these two sides of the inequality. This is our function expression. So we consider the function f going from 0 to plus infinity to r, which just does f of x is a1 plus a2 plus da 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 plus an plus x. So this is really our last of the numbers here that we consider, divided by n plus 1 minus the n plus first root of a1, a2 to an plus 1, and to an times x. So here's the x appearing. So what we need to show is now that this function is always non-negative. This is equivalent, of course, to this one. So we'll need to show f of x is bigger than or equal to 0 for all x in 0 to plus infinity. Okay. Now, how do you do this? This is now where derivatives come into play. So first of all, let me rewrite this maybe a bit more explicitly. We have that f of x is, so to see it a little better, a1 plus da 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 plus an divided by n plus 1 plus x divided by n plus 1 minus, and now this n plus first root. By our power laws that we now have established, we can rewrite this as a1 to an to the power of 1 over n plus 1, which is nothing but a root, times x to the exponent of 1 over n plus 1. So this is just a way of rewriting the function. And now we can really see, so for all x between 0 and infinity, and we've seen, okay, this is just x times some constant. This is a constant term. And this is x to something multiplied with a constant. And we know that all of these functions are differentiable. So we see that this is differentiable. And we see, we will also see that it is twice differentiable, because all of these also powers with exponents here, they are differentiable twice. With the following formulas, we can compute the first derivative explicitly. The first derivative of x is here. So this, a constant times x derived is the constant. So this is 1 over n plus 1. Yeah, this is just some constant term, so the derivative vanishes. And here we have, first of all, this factor, minus a1 times an to the power of 1 over n plus 1 times, and now we have the old exponent, 1 over n plus 1, times x2, and now we have 1 over n plus 1 minus 1. Okay, this is what the derivative here looks like. This is, we can make this explicitly, so this is 1 minus, so if we just expand this as n plus 1 over n plus 1, this is 1 minus n plus 1, so this is simply minus n over n plus 1. Okay. Now, we see that this is differentiable again, as I said, and the second derivative is also now not that hard to compute. So the second derivative of x is, so this is constant, so it disappears in deriving. Then we have this as a prefect factor, a1, a2 to an to the power of 1 over n plus 1 times, and now we've got 1 over n plus 1 times this exponent, so minus n over n plus 1, and times x2, and now the exponent subtracted minus 1. So we have to subtract n plus 1 here, which means that we get x to minus 2n plus 1 over n plus 1. And to slightly simplify this, we see we have two minus signs which cancel each other out. So a1, a2 to an to the power of 1 over n plus 1, and then we get n over n plus 1 squared times x to the minus 2n plus 1 over n plus 1. Okay, these are now the derivatives. First of all, we can see something immediately, namely from the second derivative, we see, so this here is some positive number, we don't care which one. This expression is clearly positive as well, and if x is inserted here, x is always positive, and so with the negative exponent, it doesn't matter. The result will always be positive. So this means f double prime of x is always bigger than 0 for all x in 0 to infinity. Now, the second derivative is the derivative of the derivative. So we have the statement that the derivative of some function is always positive, and there we've seen that then the function is strictly monotonically increasing. This was corollary 422. So by this corollary, it means that the original function f prime from 0 to plus infinity to r is strictly monotonically increasing. Okay, what does this help us with the original question? We want to show that f itself is non-negative. Now we can use, or we can study what happens. So what we can just do, instead of studying the whole function, we can find out if it has a minimum. And if this minimum is non-negative, then of course the function will be non-negative everywhere. So we need to find the minimum. And to do so, since we have differentiable function here, we need local minima of the function to investigate them and then to see what happens towards the end. But we have to, or kind of figure out from the behavior of the function what it does. And so we want the local extrema and the behavior of f around these local extrema. We've seen that every possible local extremum satisfies the vanishing of the derivative. That was Fermat's theorem. And since f prime is strictly monotonically increasing, it's particularly injective. So there can be at most one point in this interval where the derivative is vanishing, actually. So the local extrema, there's possibly one, but definitely not more than one. So in other words, there is at most one x0 between 0 to plus infinity with f prime of x0 is equal to 0. And we will see that there is indeed such an element x0 which plays this role, which we will explicitly compute after I erase the board. We want to find the solution of 0 is the derivative in x0, and this is explicitly given by 1 over n plus 1 minus 1 over n plus 1 a1 to an to the power of 1 over n plus 1 times x0 to the power of minus n over n plus 1. Okay, let's have a look. First of all, we can just multiply everything by n plus 1. So then this becomes 0 is 1 minus a1 to an to the power of 1 over n plus 1 times x0 minus to the power of minus n over n plus 1. Okay. Sorry, I just said something wrong. If we take this equation, bring this guy here to the other side, and then multiply both sides of the equation by x0 to the power of plus n over n plus 1. This means that this will cancel each other out, and then we would get on the other side this times x to the n over n plus 1. So x0 to the power of n plus 1 would be equal to a1 to an to the power of 1 over n plus 1. Now, by the power laws, we can just take a good exponent, namely you can just take everything to the power of x0 over n to n plus 1 and take over everything the power of n plus 1 over n, the reciprocal of this. So if we take then that this is the same as this guy here to the power of n plus 1 over n, we see that the n plus 1 and this n plus 1 cancel each other out. So the solution is here a1 to an to the power of 1 over n. So this is the only solution that we have for this equation. Now, so yeah, this just explicitly, this is the nth root of a1 times and so on to an. Now, this is the only solution of the derivative equal to 0. So this is the potential minimum. We don't know about this yet, but we have some more information about f prime, which we shall see, which we shall observe now. We have seen that f prime is strictly monotonically increasing. So, what does this mean? If we have 0 at this point, this means that in the interval left of this point, the derivative has to be negative, while on the right-hand side, right of this point x0, everything has to be positive. Otherwise, it couldn't be increasing. So as a formula, f prime of x is negative for all x in 0 to x0. So this is the interval left of it. And f prime of x is positive, bigger than 0, for all x between x0 and infinity. So what does this mean? Now we can apply the same corollary as we did before. Since we know if a derivative of something is positive or negative, we have monotonicity properties, namely again by corollary 422 that I used before to go from f2 prime to f prime. Now we use this kind of one level higher. We go back to f. Namely, this tells us that f is strictly monotonically increasing. The restriction of f to this interval here is strictly monotonically not increasing, decreasing. And f restricted to the other interval x0 to plus infinity is strictly monotonically increasing. And this helps us. Now if we imagine just a very simple graph drawing here, so assume we have here our value of x0, and we have f at some point, and remember we have to show that the function is non-negative. And we will do so by showing that f of x0 is non-negative. And if we then have these two properties here, so we know that f is decreasing here on this side, so strictly monotonically decreasing. This means that it has to come from from upstairs, so it has to be something like this or whatever, but we can never be below. And the same from here, we can only go upwards, because this is here strictly monotonically increasing, so f is doing things like this, or whatever. But we can just infer that this value here, this f of x0, that this is really the minimum of the function. So from these properties, we get that f of x is bigger than or equal to f of x0 for all x in 0 to plus infinity. So it's, with this observation, it suffices to show, to prove our inequality, that f of x0 is bigger than or equal to 0. Okay. Long computation to get here. But remember, this is a proof by induction, and so far we haven't used the induction hypothesis in the proof. This we will do now in the computation to really prove this inequality. There we really need, so here this is just a statement. Here in the proof of this inequality, we will really need the induction hypothesis, as we shall see very soon. Okay, we compute. F of x0. So, whoops. This blackboard is not really, okay. I hope it's not crashing. So by definition, by this value of x0, just inserting this into the function, by definition of the function, we just first write this down explicitly. So we have the sum of a1 to an, and then as the final summand, we have a1, a2, an to the power of 1 over n, minus a1, a1 to an to the power of 1 over n plus 1. This was part of the function. And then we have x0 to the power of x1 to the n minus 1. This means we have a1 to an to the power of 1 over n. This is x0 here to the power of 1 over n plus 1. Oh, and here I forgot to divide this by n plus 1, of course. Okay, so here we can just first of all use the power laws. This is the same as this expression, we leave it as it is, minus a1 to an multiplied with a1, to the power of n, 1 over n plus 1. To the power of, and here we just have this double power. This means that the exponents are multiplied, so we get 1 over n times n plus 1. Okay, now we can see we have two expressions which have the same base but different exponent, and now we can also combine these two guys to one exponent. Namely, this is the same, again, as this expression left as it was. minus, and now we have to add these two exponents. And so this is, yeah, let's add these exponents. I do the computation maybe here in the corner or on the other blackboard maybe. Oops. So we have 1 over n plus 1, which is added to 1 over n times n plus 1. So 1 over n plus 1 plus 1 over n times n plus 1. If we just factor out 1 over n plus 1, this is the same as 1 plus 1 over n times 1 over n plus 1. This can be put into one expression. This is n over n plus 1 over n. So in this parenthesis, we have n plus 1 over n times 1 over n plus 1. And now we see, of course, that this one and this one cancel out each other nicely. So the result of this thing is simply 1 over n. It's as simple as that. So what we get here is that this is left as it is, and here we get a1, a1, a2 to an to the power of 1 over n. Okay, so now here we have this expression, here we have this expression as well. So we can now further simplify this. Namely, this is now the same as if we just ignore this guy first and just write a1 plus a2 plus da-da-da plus an divided by n plus 1 plus, and now we have this guy divided by n plus 1 minus this guy. So we get a1, a2, an to the power of 1 over n times, and now we have 1 over n plus 1 minus 1. Okay, this is the same as this expression here, plus, so 1 over n plus 1 minus n plus 1 over n plus 1 is minus n over n plus 1, a1, a2 to an, the power of 1 over n. And now we just, here we have 1 over n plus 1 as a factor. And now what we pull the factor in front, and we pull the factor n over n plus 1 in front. Then in the first summand, so we have to divide again by n because we just inserted this artificially, and this one has been gone to the front. So we have a1 plus a2 plus plus an divided by n. And here, this was precisely the factor we had, so we get a1, a2 to an to the power of 1 over n, and this inside. And now we see, if we take a close look at this here is just the nth root of this product. So what's inside here is just the induction hypothesis. Namely, this is just the difference of the right-hand side and the left-hand side of this inequality in the case of n. So this is the thing that we assumed. So this is bigger than 0, since this guy here is always bigger than 0, and this is, of course, a non-negative factor, by the induction hypothesis. So just when we thought it would never appear, it finally appeared in the end. Here we need the induction hypothesis. So since this expression here is then non-negative. So we've shown that f of x0 is bigger than 0, and so we derive from this that f of x is bigger than or equal to 0 for all x in 0 to plus infinity. And this is what we wanted to show. And this finishes the proof of the inequality. This was quite some work, but this is a nice example of how you can really use derivatives in a smart way and to use these monotonicity consequences and so on, and to really work with derivatives to derive some beautiful results. This inequality has some additional statement, namely, there's the additional statement which I've included in the lecture notes, that equality holds in this equality if and only if all these numbers a1, a2 to an are the same. This part I've left out of the proof, but you'll find it in the lecture notes. So this is just a slightly bigger statement in the lecture notes. Okay, so much for this one, and now we go towards Taylor's theorem.